So I have a slide that shows the Berkeley faculty who are in this field. You're not on the slide, but should you be? Okay. He's got a toe in the water. Okay. Say again?
Do you have Borelli on the slide?
No. Where's he from? Oh, no, I don't. And yeah, I understand there's a mechanical part to this. Yeah.
No, I mean, he has an interesting approach to solving convex optimization problems
Yeah.
with Kirchhoff's laws.
Yes.
I worked with him for a little while.
Okay, so it's definitely related. Yeah.
Networks of R's and C's.
Yes, that'll do it.
Diodes
That'll do it. That'll do it. Yeah.
satisfies KKT conditions.
Yeah. Okay. So save up your questions. You're obviously very knowledgeable.
Good afternoon, everybody. It's my particular pleasure and honor to introduce my good friend, Eli Yablonovitch. Eli is a proud alum of McGill University, where he did his undergraduate work, and Harvard University, MS and PhD. Eli is famous for many, many things. He is the originator of the concept of strained semiconductor lasers, strained layer epitaxy for semiconductor lasers, which are used in all the lasers that are out there in our optical communication infrastructure. He's also was the inventor or the discoverer, not sure which, of photonic crystals, also which now has kind of expanded into the whole field of metamaterials. He's also made some very fundamental contributions and held the world record for solar cell efficiency for many years. Still. And he's also, by the way, a member of the National Academy of Engineering, the National Academy of Science, the National Academy of Inventors, the Royal Academy. He's quite many other awards and accolades, and I could go on, but I think you'd rather listen to Eli, so I will turn it over and introduce Professor Eli Yablonovitch.
Okay, thank you. So thank you all for coming. I'm actually very excited about this topic, so I like to jump at every opportunity to discuss it. And this first slide, actually I should go back to my students here. A lot of this work was done by my students who have graduated, they've moved on. So Patrick Zhao and Sri Vadlamani, and you'll see their specific contributions as I go through the talk. Now, the main part of the talk is on the first slide. So if you come in late, you're going to miss the whole point of the talk, okay? So everybody has to, I mean, to get here, you have to take a physics class. And you learned certain equations in physics, like F equals ma, or maybe you learned the Schrodinger equation also. And so those equations, they're equal. It says F equals ma, etc. Now, but there's another way to express the laws of physics, and that is to express them as inequalities. So you have to get a little deeper into physics, and then they start expressing these laws as inequalities. They're equivalent to the normal laws. It's just another way of expressing the laws. Now, if you have an inequality, let's take, for example, physical annealing. This is like the first thing you learn in chemistry is that a system drops to its lowest energy level. So it's an inequality. It's going to keep going down, down, down until it reaches its lowest energy level. So if you think about that for just a second, you say, well, it's doing some kind of optimization. Indeed, the energy function is something that you can optimize, and the system will represent the energy function, and you'll have a physical machine that solves a problem of optimization. The optimization is, how do I find my state of lowest energy? You just wait. Okay, now, but it turns out that throughout physics, there's a bunch of these inequalities. And every one of these inequalities is capable of solving an optimization problem. And so what it says is that, and I never realized this, and part of the reason I'm excited now, is that without any extra effort, physics does optimization for you. And so let me give you some more examples. Dropping to the lowest energy level, okay, that's a pretty good example. But if you're an aficionado of the Feynman lectures, it'll be the principle of least action. So Feynman is very fond of the principle of least action, but it can also be restated as the principle of least time, which is a principle in optics that was actually discovered over 200 years ago, and that it says the light ray will follow the path that takes the least time. So, interesting. Then there's another optimization method. You have lasers. It's very common to have multi-mode lasers, and then it finds the mode with the lowest loss. And so you get that sort of for free. The variational principle is a principle that you can adjust a wave function until you get the lowest energy. And then there's the adiabatic method. I'll kind of explain the adiabatic method on one of my slides. And then there's this one, which I have decided to give it a name it after Onsager. So Onsager was a theoretical physicist, and in 1931, he put forward the idea that if you have a driven system, where there's, for example, there's electricity coming in, which pretty much accounts for this entire department. If you have a driven system, that system will automatically, the currents will branch in such a way as to dissipate the least amount of heat. So that's pretty good. Now he has a kind of fancy name, so you might be put off by the name, but he calls it the least entropy generation, or the least power dissipation. This is totally non-obvious, by the way, and the proof that it's non-obvious is that it remains controversial to this day that systems really behave this way. However, he did win the Nobel Prize for something that he used this for the derivation. So that's probably meaningful. Okay, now what about optimization? It's sort of everywhere, and deep learning is like the hottest thing in computer science, and it's an optimization problem. You have to adjust all the matrix elements so that when you do a matrix multiplication on a photograph, out will pop out the answer that you're seeing a dog, for example, or a cat, and those will be very different, of course. So through everywhere there's optimization. For example, control theory. Let's say you're flying an airplane, and you have so many things you can adjust, and you can adjust them every few seconds. So you have 100 or 1,000 variables that you have to control, and you're trying to get the airplane to follow a certain path in space. Many other things: circuit wiring, protein folding, packing. This kind of reminds me. Before we had SUVs, we had regular sedans, and there was always a challenge on vacation getting all the suitcases in, and so that's regarded as a hard problem. So what is a hard problem in computer science? They call it NP hard, but the meaning is that the way you solve the problem, the only known way of solving the problem, is to try every possibility one at a time, and eventually you'll hit the right one. And so that's regarded as very hard. Now, they used to have the traveling salesman problem. That's obsolete now, has been replaced by the Amazon Prime problem. Okay, and so this is something every morning, 40,000 trucks go out. They have 100 stops to make. What is the sequence of the stops? It's regarded as a hard problem, similar to the traveling salesman problem. And then in finance, you do it, and in scheduling of airplanes, and optimizing bridges and things in civil engineering, and in aerodynamics, et cetera. So optimization is worth the trouble. So what I'm going to say is that physics does the optimization for you, because physics has all these inequalities built in, and if you just use those inequalities, you'll arrive at some kind of an optimum. So here's one that is the principle of least time, but the analogy is with a lifeguard. So the lifeguard has to save a drowning swimmer. What does the lifeguard do? Goes as far as possible along the sand, because she can run faster on the sand than she can swim, and then she jumps in and is taking the least amount of time to reach the drowning swimmer. Well, that's exactly what light rays do. Light rays, they travel in a low index medium, and so they go fast. Then they go into a high index medium and they get refracted. And so you can derive Snell's law from this principle of least time. So that's kind of interesting. Least action, of course, is more common in physics, because least time is too easy, but I thought I'd start with that one. Okay, now here's one that is going to be our most important one. Suppose you had a circuit with two branches, and the two branches would be identical. So you'd figure the current would divide equally between the two branches. But if you saw them divide 1/3, 2/3, you'd know there was something wrong. And in fact, the circuit, if you start off like that, the circuit will evolve rather quickly, and it'll give you half and half. So it'll equalize the two branches. And so and when you equalize the currents, that's the condition of the least heat generated in those resistors. So you have these resistors, and you don't want to generate much heat. And so the circuit automatically figures that out and readjusts the currents to make that happen. So this will turn out to be our most useful physical inequality. Okay, here's one that's kind of interesting. Is laser people would be very fond of this. You have a laser cavity, and maybe it's lossy, but it has the lowest losses down here. And there's one that's almost as low. But what happens when you try to run this, see if I can run it again. So the laser energy will all go into the very lowest one. It will avoid the second lowest one. And so the laser itself will find the electromagnetic mode that has the lowest loss. So that's a form of physical optimization. Here's one that is in quantum mechanics, and that is if you have a wave function, it just happens to be the wrong wave function, and you calculate the energy, that's the red one. So it's that red one. And then you have to keep readjusting it. And as you readjust it, the energy gets lower and lower. And when you've reached the lowest energy, then you have the green one, which is the true wave function. And so just in the course of quantum mechanics, systems seem to automatically adjust their wave functions to give you the least energy. Now, here's the one that I called physical annealing, which is sort of easy to understand, because what happens is you try to get to the lowest energy state. We all know that. The way in which it gets interesting is that you get stuck before you get into the lowest energy state. You might get stuck here, and then you get out of that, and then you might get stuck here. And if you're very lucky, you fall into the lowest energy state. So this is one of the problems, And I know that if there were some serious theory of computing people here, they would say, well, you can't guarantee that you'll get the absolute lowest optimum. And that is true. All of these physical methods have the same problems as all the other methods in computer science. They tend to get stuck, and then you have to have some techniques to get them unstuck. And mostly you insert noise. If you insert noise, it'll jump out again, and you have a better shot, and then you have another shot. Okay, so that one is physical annealing, but as easy as that one is to understand, nobody uses it. And I think the reason they don't use it is that if you go to the let's say you have a circuit, you go to the lowest energy state, all the currents are zero, there's nothing to measure. And so it's a great principle, but it seems to be very slow, and then at the end it's hard to know what you ended up with. Now here is one that is a very popular one, and I forgot to put the name of the company, D-Wave. So D-Wave claims to have a quantum computer, but they're doing something which is sort of known, and it's called the adiabatic method. So let me give you an example. And by the way, you don't need quantum mechanics for this. You just need your freshman electrical engineering, because you can do this with inductors. So with the inductors, you have maybe they're all cross-linked, so it's very hard to figure out what is the lowest or the lowest frequency configuration in this case. And so we say, okay, this is the lowest frequency configuration. Actually, it's not hard to solve, because you turn off all the interactions. And then what you do is you start turning on the coupling inductances. So these are the coupling inductances on the horizontal axis. And as you turn them on, what happens is an avoided crossing. Now, these avoided crossings, you also learn this in quantum mechanics. But you don't need to take quantum mechanics to learn about avoided crossings, because it happens with inductors. It happens in the classical world. And so as you gradually turn on the interactions, it gets to be a very hard problem. But the system sort of solves it for you. It stays in the lowest frequency state. And all the wrong states end up at higher frequencies. So that's somewhat popular because it is done by D-Wave. D-Wave claims they have a different name for it. They call it quantum annealing, because they want to pretend it's quantum. But I think I just showed you that it isn't. But it could be. But their machine is it's too many disturbances. It's no different from doing it with inductors. And so this is sort of an example. You have many possibilities. You turn on the interactions. The problem gets to be very hard. But the system solves itself for you. And D-Wave has had a lot of mileage from their system, calling their system quantum. Okay, so which of these is best for doing optimization? So we're all engineers, so we need to find the best approach. So I can tell you the only approaches that have been used are this Onsager approach, and the other approach that has been used is the adiabatic approach, which has mostly been used by this company called D-Wave. Okay, so let's kind of illustrate a little bit. Well, I already illustrated this. Yeah, these are just the two that people use. The Onsager principle, the principle that the currents will adjust themselves, branch out in the branching circuits so they dissipate the least amount of heat. And that's, in this particular case, it's when they're equal. And the adiabatic method, which I already showed you. So those are the two methods that people have actually published on. By the way, I like to get questions, because if I don't get questions, only the professors in the front row will understand me. Okay, so I need to know where your mind is, so I can. Yeah. P is the interaction. So maybe I should have used a different symbol. It's just a parameter in the Hamiltonian. So this is actually quite important in this adiabatic method, is how fast you turn on P, because if you go too fast, you don't get the avoided crossing, you jump right across, and so forth. So I think you've given me a good reminder not to use P, because P is momentum, and I should use something different. Okay. Say again? It's something you turn on in the Hamiltonian. It's the coefficient of the inductors that are coupling it and making it a hard problem. Okay, so people get confused because it has the word entropy in it. So this is not thermodynamics. This is not going to the lowest energy state. This is not going to the state with the maximum entropy. Okay, so that's regular thermodynamics. So this is the flow. Regular thermodynamics, you maximize the entropy. The Onsager principle is different and a little bit controversial, because in regular thermodynamics, you leave the system alone, it's supposed to fall into the lowest energy state. However, our circuits, every circuit that I know of has a power supply. So you have continuous power input. So this is not going to be in your thermodynamics book. And what the Onsager principle is telling you is not that the entropy goes to a maximum, but rather that the time derivative of entropy goes to a minimum. And the point there is, or the extremum, it's in one case you're dealing with entropy, that's equilibrium, and in the other case you're dealing with the rate of change of entropy, in other words, the heat generation. And as I mentioned, Feynman liked this, the Onsager principle, and it's in the Feynman lectures. But he didn't use the name Onsager for it. Okay, so let's say we want to make a machine. Actually, and you'll see that many groups have made machines like this that try to solve a hard problem, an interesting problem. And one of the great truths of our society is that if you get an answer, you mostly want to get a digital answer. So what should your machine be made of? It should be made of bistable elements, so they will be like a flip-flop. Flip-flop actually is an analog device, but then you treat it as if it were digital, but it's actually, it's a machine, it's a little machine in and of itself. So you make up all these bistable elements, and maybe each one is easy to solve, but when they're all coupled together like this, it's hard to solve, and you want to set it up so that, for example, if you're going to use the Onsager principle, you're going to set it up so the heat dissipated in the resistors is going to be the function that you're trying to minimize. So that's sort of a rough diagram. Now, let me give you the example of the problem. Almost everybody wants to solve this problem, and it's a very easily stated problem. If you have a bunch of kitchen magnets on the kitchen table, how do you arrange the magnets to have the least amount of energy? And so it turns out that's a very hard problem. Very hard means the only way to do it, just try every combination, a little bit like packing the suitcases in my trunk. That's rather hard. So you can say, well, you're trying to minimize the energy, and you're gonna do it with a circuit where you translate the energy into the heat dissipation. So it's really time derivative of energy that we're interested in. Actually, no, in this case, it's energy we're interested in, but we're going to translate it to time derivative of energy, or heat. So our own Professor Richard Karp, who's the most distinguished member of the faculty of the EECS department, he is very famous in computer science because he showed that if you could solve the Ising magnet problem, you could solve at least 21 other problems in computer science. And let's see, job sequencing, that's the Amazon Prime problem. Max cut is similar to the Ising problem, etc. They're all kind of weird, hard problems that the only known way of solving them is by just trying one thing after another. Okay, so that's the reason why people like to deal or prove that they can solve the Ising problem. Now, I want them to be bistable because I want a digital answer when I'm done. So there are many bistable things out there. But a lot of papers have as their bistable thing something called the parametric oscillator. It's a very strange oscillator in that, it actually has gain, but it only has gain for cosine. So if I'm in the complex plane and I have the sine omega on the vertical axis and the cosine omega on the horizontal axis, this gain only multiplies or gives you gain for cosine waves, but actually gives you sort of what's called de-amplification for the sine waves. So then you let it run, and all you need is a time-varying capacitor, which you can get from a varactor, and you want the capacitor to oscillate at 2 omega, and it's going to give you gain at omega. So this is quite famous. People get excited about this, but I discovered that this was first proposed in a paper by Lord Rayleigh in 1887. So this is, of course, he was doing it for a mechanical system and not an electrical system. But so it's a way of getting a bistable component. So each of these little oscillators is a bistable component. Can be either plus cosine or minus cosine. That would be the red and the blue oscillations. And it's gain, so it builds up. Cosine wave builds up, and then it saturates. And that's your 1 bit, because it could either be positive or negative phase. This is actually quite handy, because if you think about it, the only difference between +1 and -1 is just a shift in time. So it's like time multiplexing your answers, and which means it's exactly the same physical system. So +1 and -1 are identical, they're just time shifted. It's sort of interesting. Yeah, go ahead. Yeah, don't put random phases in there, because that's your information. Right. You have a clock. So let's go back one. So you have you start with 2 omega, and let's see, I guess it was on the previous slide. So you have to oscillate the capacitor at 2 omega. That sets the origin of time, and then the rest of it, we call it sort of a phase shift. It's either 0 phase shift or it's pi phase shift, and that's just a shift in time. And that's and oftentimes people in this field, they like the idea of using time shift to encode the information. No, each oscillator will develop either a plus cosine wave or a minus cosine wave, and that's going to end up being your answer to your unsolved problem. So let's give an, so the claim then is, this is just one example, by the way, because there are, I'll show you that you don't have to use oscillators. There's other ways of doing it. So, but this is a popular way. So you have 2 oscillators. They're either in phase or out of phase. Now, you want to force them to be maybe in the interaction. Sometimes you'll be forcing them to be parallel, sometimes anti-parallel. So if it's parallel, you use parallel wires to connect them, or parallel resistors to connect them. Then there will be a tendency for them to oscillate in phase. Or you could couple them with crossed resistors, and the crossed resistors, they'll oscillate out of phase, and but that's exactly the same as the magnets, because the ferromagnetic would be in phase and anti-ferromagnetic would be out of phase. Of course, there's no magnet here at all. We're just building an analogous physical system that has the same properties as the magnets. So the magnets are very famous. So who is doing this kind of work? We have, for example, here in our department, Professor Jagjeet Roy Chowdhury. He's quite a pioneer in this field. He sets up the circuit. He doesn't talk about parametric oscillators. He talks about injection locking, but the injection locking signal, if you Fourier analyze it, has 2 omega in it, and once it has 2 omega, then the rest of it follows just the same. So then he just lets it go, and it settles down, and some of them are 0 phase, some are 180 degree phase, and that's your digital answer. So it's quite amazing. And so let's go on with some more examples. So the examples I'm going to show you is that there are many people who have started doing this in the past 2 years. And each group is convinced that they have some secret sauce and that they're the only ones who are doing it. But in fact, I'll try to indicate that they're all doing the same thing, which is they're following the Onsager principle, and maybe they're not 100% aware of it, that there are other people that they're not even aware of that are doing the equivalent thing. So I'm going to show you some groups from around the world. So that was Berkeley. Here is Cambridge University, And this is kind of interesting because you have these little vertical cavity, they're not exactly lasers, they're little electromagnetic resonators. They're like two mirrors, one above one another, and you can excite them, you can monitor what they're doing, and so they have some fringing fields here. They tend to interact, so you can get them to mimic the magnets, and then you just let them run for a little while, and they will collapse. Some of them will be a positive phase, some will be negative phase, and you get the answer. Now the problem is they thought this was so important, they ran this at 4 degrees Kelvin. It's the only way that this particular technique runs. Of course, I don't know what the reaction is because people are getting similar results with a much simpler approach. But this is one way of doing it. Here is an approach from Stanford, Professor Yamamoto. It is the parametric oscillators, but boosted from radio frequencies, boosted all the way to optical frequencies. He is a heavy user of time multiplexing, so each of these pulses represents a bit, and the bit will either have 0 phase shift or pi phase shift, and he needs them to interact. Well, that's not too convenient. He has to put it through a field programmable gate array, etc. But eventually they interact, and he's amazed because it actually solves some of these very hard computer science problems. Now here is another approach from MIT, and this is kind of a neat one. It uses silicon photonics, which I'm kind of fond of, and what it does, you have these waveguides in silicon, and you can mimic any kind of unitary matrix. So you make unitary transformations, and then you go through a nonlinear component, which is what you always do in deep learning, and then you send that back to the input and keep iterating it over and over again, send it back again, and it also solves these hard problems. Each of these waveguides will then develop either a 0 phase shift or a pi phase shift, and they'll give you a digital answer to a problem. So they, of course, think that their approach is the only approach. Okay, here's one that does not rely upon oscillators, because there's some people really strongly believe in oscillators, but here's an approach without oscillators. This is being done by Professor Saif Salahuddin in our department, but it is his thesis advisor is actually coming here to give the solid state seminar on Friday, and he will tell us more about this. But basically, the bistable element is basically a high gain transistor, which we often call comparator. And the property of these high gain transistors, either they go all the way to the positive rail of voltage or they go all the way to the negative rail of voltage. They keep readjusting. And you need a little bit of noise for all of these things, because you need to wander around a little before it locks into a solution. And so you feed them back, you feed it back through an array of capacitive couplings. And so you have a matrix of capacitors, and you have the feedback, and let it run for a little while, and boom, it gives you an answer to a very hard computer science problem. So this shows that you don't need oscillators, although they're popular. And here is an approach from Professor Kulkarni from the University of Texas, and it looks like a normal logic circuit. You have it is similar to the other one. You have just a logic gate, and you don't know if it's going to be 0 or 1 or positive or negative, and you just interact with all the neighboring gates, and they kind of vote, and it tells you whether this is going to end up as positive 1 or negative 1. And now, I mentioned this to Professor Salahuddin, and he said, well, it's not going to work because there's no noise. And then you go back and read the paper. So here's the reference to the paper. Yes, they're constantly injecting noise. So you have to, as you wander around in the solution space, which could be a huge space, could be a 100-dimensional space, as you wander around, you'll sometimes get stuck, and you need to constantly inject noise to get out of the places where you're stuck. But the point is, some very simple things seem to work. And let me kind of summarize. There are at least 20 groups doing this worldwide. And here at Berkeley, we have at least 3 faculty, but I just heard that there's another professor who's doing this in mechanical engineering with a mechanical system. The similarity of all these systems is that they are all readjusting themselves to lower the heat dissipation. This is the one that I'm fond of, but there are many other ways of doing it. Now, so what we did, this was my student, Patrick Zhao. He went and he did this with 33 different magnets. Well, each magnet was actually just an LC oscillator, and with a little bit of gain from the capacitor oscillating at 2 omega. And so he connected them all together. This is a little bit extreme. So you can't see all the connections. Some of them are blue. The ferromagnetic ones are blue, and the antiferromagnetic ones are red, but you can see it's just a mishmash. And he's got his little oscillators are all around the periphery, and the interior of the circle is all wires. And then he restricts himself to 32 spins or 32 magnets. And the reason is you can still do exhaustive search. Its problem is big, but it's not so big that you can't go through one by one all the possible answers. And I believe that the one he was solving, this was the final answer, which is kind of amazing because there are over a billion possible solutions. Let me show you how the circuit works. Okay, you turn it on, and you have this parameter gain, so you're not sure how much gain to put on, so you slowly ramp the gain. And the oscillators, all these different colors down here, represent oscillators, and eventually they lock into a positive phase or a negative phase. And this sort of shows you how it locks. After about 400 nanoseconds, it locks, but these were oscillators oscillating at 1 gigahertz, but with a bandwidth of 100 megahertz. So the clock period was about 10 nanoseconds. And after about 400 nanoseconds, the circuit settled down and gave you the answer to this very hard question. So what is amazing to me is that you had to search through 2 billion possibilities, and it took you only 20 clock cycles or thereabouts. So it's quite remarkable.
Did he actually build the circuit, or did he simulate it on the computer?
That's a very good question. And this is one of the contributions of Professor Jagdishwar Chowdhury. He started simulating them, which of course is much less work, and you can learn a lot more in less time. So the SPICE simulation is perfectly adequate. However, I was at Intel last week, and they warned me that when you have real components, you have real parasitics, and it's sometimes the simulation doesn't quite work out. But this is sort of an example of what you have. You see blue dots on this slide, and this is my student Patrick Zhao. So you have the blue dots. The blue dots represent the solutions to the problem with the 32 spins, or 32 LC resonators. And then you're trying to find an energy. Now, most of the things you try, you can try many different things that all have the same energy. So all those blue dots will pile on top of each other. So each of these blue dots could represent 1,000, maybe even 1,000,000 different answers to the question. Of course, the answer to the question, you want the one that has the lowest energy, and that there's only one dot down here. So basically, what the circuit did is it went through all of these over 1 billion possibilities, and it homed in on this one in about 20 clock periods. So this gives you sort of a physical feel for what's going on. So let me summarize: is that there are many schemes out there. I believe that they are all using the same physical underpinning, but there's nothing easier than making circuits. There's nothing more scalable than making circuits. So I think the real world is converging on circuit solutions, sort of like this and like this. And let me show you some examples of that. Oh, first I have to show you that the Defense Department got kind of excited about this, and they put out a competition to make these things. So this is, but the program manager, he likes quantum, so he called it quantum inspired, but at least he had the word classical in there. So I regard this physics-based computing as being an intermediate step toward quantum computing, and that quantum computing will take a long time. And in the meantime, we're going to have amazing problem solvers that are based on physics that will come much earlier. So they have that. And I should also mention, I was at Intel last week. They have their own. They're giving their own grants in this field. So the field is sort of taking off. Here's a beautiful result from Professor Chris Kim of Minnesota. And so what he has, like every good chip designer, he knows how to make a ring oscillator. So he made, on this slide, you see 2,000 ring oscillators. Okay, and they were only coupled to the nearest neighbors, so that's easy to do. And then he said, let them organize themselves. And they organized themselves into these rather beautiful spirals. So these spirals have a name. They're called skyrmions. They're known in magnetism, but you know, there's no magnetism here. This is all just ring oscillators, and you're trying to fix the phase of the oscillators, a zero phase or pi phase. And he just let it go, and it settled into the skyrmion pattern, which is well known in magnetism, but it's sort of, obviously, he was doing a pretty good job of mimicking magnetism. And so I think we already said what's the best for doing optimization by the vote of the researchers out there. They're almost all doing Onsager's principle. Of course, they're very jealous about what they're doing. They hate to see it reduced to some principle that other people can do, maybe in an easier way. And the adiabatic method is also. These are the two that are working. Now, the others, like principle of least action, we just need to figure out how to use it. They might work out, and even physical annealing might someday work out. So we were getting some results here, and they were kind of interesting. I showed you the example that we like is the parametric oscillators, radio frequency, and I was browsing online, and I saw an oral history from a very famous scientist from IBM, Rolf Landauer, and he was joking. He was being interviewed in oral history. He was joking how von Neumann hoodwinked IBM into paying millions of dollars for an alternative to transistors. So let me bring you up to date. So 1945, the end of World War II, and von Neumann kind of explains how to build a computer. It's called, and every computer has had that since then. 1945, von Neumann architecture. But he thinks a little more deeply, and it was a moment, and it was all done with vacuum tubes. It was a moment in time, it was 1954. The transistor was 6 years old. No one was sure what it was good for, except maybe radios. And so he says, well, I don't know about transistor gain, but I can get gain with parametric amplifiers. So he patents, von Neumann, who's regarded as a genius of the 20th century, maybe second only to Einstein, he patents the parametric amplifier, exactly what I was describing. You can see he's got the capacitor and all this great stuff in the patent. And it has this sort of, you can build entire logic systems. So he proposed a logic system based upon the bistability of parametric oscillators. It was the early computer days, so everything had to be bistable. So it tends to solve a problem. And the problem is that it does require quite a bit of voltage to turn a transistor on and off, close to 1 volt. And this is, we just had a a big NSF center to try to solve this problem. We didn't solve it, but we defined how difficult it would be to solve it. It's quite difficult. Okay, so we're in a world where your chip in your cell phone, it requires close to 1 volt, maybe 0.8 of a volt operating voltage. And that's a pity because they could run at much lower voltages. So I asked Dr. Sri Vadlamani, one of my students, I said, why don't you see how low the voltage you can have on the parametric oscillators and still get the right answer? And he used SPICE, and SPICE includes noise, and so he included the noise, and he ran it at 100 millivolts, and he got pretty good. So this line is 99% of the best known answer. Okay, so this is a problem big enough, 800 Ising spins. Nobody really knows what the answer is. So then he lowered the voltage, 10 millivolts, 1 millivolt, still giving good answer. 100 microvolts, oh my God, 50 microvolts. And so, and the noise was around 5 microvolts, the RMS noise. So there was down with a very poor signal-to-noise ratio, and he was still getting good answers, which is kind of amazing because if you follow this approach, maybe this is a way to reduce the voltage and power requirements. So just to give you an idea of among the things you can do with this, you can do linear regression, which is also an optimization problem because you're trying to fit and have the minimum errors. But this is only 2-bit accuracy. You can see the circuit is already getting quite complicated. So it's still a bit of a challenge. But the energy consumed, so you have to be careful because these are constantly being fed with voltage. And so what happens is you'll never be efficient unless you turn them off. Once you get the answer, you turn it off. And this sort of an answer. This is the power consumed by the circuit, and eventually settles down. And the area here, it represents the total energy consumption. As long as you turn it off once you get the answer, it's very efficient. So optimization, I've been giving examples. It's a fine accomplishment. A lot of people are doing it. There are startups, and it's well on its way toward commercialization, but it's a somewhat specialized function. And I was thinking to myself, if this is going to have the biggest possible impact, you've got to do something about general purpose computing. And so you go back to von Neumann, and he says, well, maybe we can do that, because these circuits were parametric amplifier circuits, so we have to go back and look at the patent. The patent is extremely hard to understand. There was a follow-up paper. He died right after he filed the patent. There's a follow-up paper that tries to explain what he did, but it's still a little bit up in the air. But this sort of an example is you can make an AND circuit out of the parametric oscillators. All the normal logic functions you can make, and there's a chance they might work at really low voltage and might make even a bigger impact than just optimization. And so this gives you an idea how low a voltage. I mean, this is sort of unbelievable that you're getting good results at only 50 microvolts. So now, but here's a nice feature. If you're working at a very, very modest signal-to-noise ratio, your logic circuits become reversible. And so there are great advantages in computer science to have reversible logic. So let's summarize here. We have people have made chips with 10,000 bistable elements. They're not fully connected though, but they don't have to be for a lot of problems. So, but the real question is, what is going to be the near-term application that pays the money to develop all this stuff? So these big chips cost a lot of money to make, to design. So what's the advantage of these types of circuits? They are very, very fast because you don't go through all the normal steps in a computer. You just let it go and it gives you the answer right away. And also they consume about 10,000 times less energy to solution than a normal computer. So where are the possible applications? So it should be an application, and this is where anybody can think about what the application should be. maybe it should be control theory, because let's say you're flying an airplane, you need answers right away, you need to optimize right away. So that's one possibility. You could contribute toward artificial intelligence. That's a little hard because they have so many variables that enter into those deep learning programs. They could have a trillion different constants. So maybe that one's not a good one. Here's one that's kind of interesting, is workflow, optimizing the workflow at a data center. There's a huge amount of stuff going on at data centers and a lot of money tied up, and it's sort of like the traveling salesman problem, is that which job gets done first, in what order, is subject to all the constraints. Another one I heard recently is military, and that is that if you imagine that people are throwing rockets at you and you want to shoot them down, but you have limited resources, and you have to, so it's a big optimization problem, and you got to do it right away, okay, because the rockets are flying toward you. So that would be an interesting one. So all these are nice optimization problems, but I'm hoping that there's a way to enter into general purpose computing. So thanks very much for listening.
We have time for some questions. Anybody have any questions? You need to talk into the mic because this is being recorded.
Oh, this is
That's a microphone, believe it or not.
great. So, how about reproducibility of these results? In a sense that you build one chip, let's say like an oscillator example, it will exhibit a certain set of patterns depending on the parasitics, the voltage of all the threshold transistor variations of that particular chip. Next chip is not going to give you exactly the same pattern unless you can bid it. Maybe it's just for combinatorial problems.
So you have to think a little differently about these sorts of problems. Actually, not only will the next chip probably not give you the same answer, but if you ran the same chip a second time, it'll probably give you a different answer. And that's actually regarded as good. And the reason is that you can't quite guarantee an optimum anyway. And so sometimes it's good to show that multiple answers are reasonably good. So it's a little bit like real life.
Over here?
So I noticed earlier in one of your first slides, you mentioned the first threshold kind of example.
Yeah, there was one approach toward optimization, yeah.
So, and here you're sort of like converging to some solution, right?
Right.
You're not sure exactly what. My question is there some sort of approach for you to explore sort of like a more than just the, for instance, if I'm trying to find an eigenvalue or an eigenvector problem, once I found with power iteration, once I found the biggest eigenvalue, I just chop it off with orthogonalize it out, and then I can operate on the remaining space. Is there some sort of like general equivalent to that kind of process here?
That's a good process, and that indicates that there are competitive techniques. For every optimization problem, there already exists some methods, and so you have to find exactly the right application to pay to build up this technology.
Okay, last question.
Oh, it's a fantastic. Get it so many different fields. It's just, thank you very much. I'm wondering about the von Neumann oscillator. The capacitance and the resistances is where the two variables is where the noise is coming in. Is that correct? And what kind of noise?
Well, noise comes from resistors. So this is part of physics. Is every resistor generates noise. And the example I gave, that if you had signals, let's say of 25 microvolts or 50 microvolts, you could tolerate noise of 5 microvolts, which is kind of amazing.
Yeah, but the capacitance had a variable on it too, a variable hour.
That's how you have to drive it, yeah.
Do you change that during
Yeah,
the
you
operation?
oscillate the capacitance at 2 omega in order to get gain at omega.
So you're changing the capacitance continuously during their operation? or
You're oscillating the capacitance.
Oh, you're oscillating,
Oscillating
and
it
then
back
the
and
resistor
forth.
does it by itself.
Yeah.
Got it. Thank you.
Okay, well, thanks. Let's thank the speaker for a really interesting talk.